Hi, my name is Ajay, and this is our ICRA 2020 presentation on our new algorithm for offline reinforcement learning called IRIS. Large-scale supervision has accelerated progress in other fields, but policy learning has witnessed no such success. However, there have been recent efforts to bring large-scale supervision to policy learning in robotics. New supervision mechanisms allow for collecting thousands of task demonstrations in a matter of days. This is from prior work where we built a system that allows remote workers to teleoperate robots in real time with nothing but a smartphone and a web browser. We used it to collect a large pilot dataset. Large datasets such as this one motivate the following question. Can a robust and performant policy be learned purely from external experiences in a dataset? Let's say we are given a large collection of varied task demonstrations. Our goal is to use this large amount of data to learn a policy that accomplishes the task without collecting additional experience. Learning in this setting presents two key challenges. Large datasets can exhibit suboptimality and diversity. I'll show you some examples of both from the RoboTurk pilot dataset. In this example, the robot fumbles around with the can before successfully grasping it. In this case, the robot misses the can multiple times while attempting to grasp it. Here, the robot tries to pick up the can sideways and initially fails. Here, the robot tries to approach the can from the top to grasp it, but it misses. In this case, the robot has trouble placing the can in the bin. In this example, the robot gets blocked by the wall. Data diversity can also make learning policies from large datasets challenging. Task instances can be diverse. There's a great deal of variation here in the initial can and robot locations. The solution strategies can also vary significantly. For example, here the robot carefully approaches the can from the top to grasp it. Another solution is to slide the gripper into the can sideways to grasp it. Here, the robot partially tilts the can to grasp it. Here, the robot completely tilts the can over and then grasps it from the top. And here, the robot completely tilts the can over and then slides the gripper into the can to grasp it. In this case, the robot uses the wall as a support point to aid in grasping. To overcome these issues and enable policy learning from large datasets collected by humans, we developed Implicit Reinforcement Without Interaction at Scale, or IRIS. Our main insight is to decompose a policy learning problem into low-level goal conditioned imitation and high-level goal selection. The low-level controller is trained to imitate short sequences from the demonstration data. The last observation is treated as the goal. Thus, this controller is able to reach nearby goals. The high-level goal selection mechanism consists of a generative model that proposes goals and a value function that is used to pick the best goals. At test time, given an observation, the high level selects a new goal, and the low level is then unrolled for t-time steps to try and reach that goal. This process repeats. Now I'll explain how IRIS is able to account for both suboptimality and diversity. IRIS is able to learn from suboptimal demonstrations by using the value function for goal selection in order to pick the best goal at each time step. IRIS also accounts for diversity in the demonstrations. The generative goal model captures the diversity in the demonstrations, while goal conditioned imitation helps reproduce specific parts of demonstrations. Now that I've outlined the algorithm, I'll talk about how it differs from prior work. Policy learning without interaction is not a new concept. It's often referred to in the literature as batch reinforcement learning, or batch RL. The goal is to learn a policy from an offline dataset of state, action, and reward transitions. Several recent works have shown that they can recover good policies in non-manipulation domains, such as locomotion and Atari. However, They usually evaluate on data collected by a partially trained RL agent instead of humans, who can generate far more unstructured data. They also assume access to a dense reward function, allowing them to distinguish good and bad behavior more easily. A concurrent work did apply BatchRL to manipulation, but only a subset of their data is from humans, and they used a reward sketching interface to annotate dense rewards in their dataset. By contrast, our algorithm works on robot manipulation domains, is able to leverage offline, unstructured datasets generated by several humans, and only assumes sparse task completion rewards. We evaluate Iris on 3 datasets. The GraphReach dataset was procedurally generated by sampling suboptimal paths from a start location to a goal location. The ideal algorithm would realize that the best path is a straight line. The RoboSuite Lift dataset was generated by one human who completed the task inefficiently, such as moving the arm aimlessly before grasping the cube. The last dataset is a Robotorque crowdsourced dataset. We compare Iris against a behavioral cloning baseline and batch-constrained Q-learning. Behavioral cloning uses supervised learning to try to learn to output actions in every state. Batch-constrained Q-learning is a recent BatchRL algorithm that learns a Q function from an offline dataset and uses it to extract the best action at every state. We see that Iris is able to achieve 80% success on the lifting task and 30% success on the crowdsourced CANS data, vastly outperforming the other baselines. The experiment results from the last slide were on low-dimensional observations. Here we show that Iris can also learn from pixel observations. We apply an unsupervised learning algorithm to pre-train a landmark representation using unsupervised foreground-background segmentation. The learned encoder predicts 16 landmark pixel locations for each image observation. We then train Iris using this landmark representation. Surprisingly, we were able to achieve significantly higher performance on the Robotorque crowdsourced dataset using these pixel observations. Here, we show the average success rate as a function of wall clock time on our 2 manipulation datasets. The top 3 performing learning curves that you see are variants of Iris, with the lifting dataset to the left and the CANS dataset to the right. The primary difference between the green curve and the purple curve is the use of goal conditioning. Thus, goal-conditioned imitation, which the baselines lack, is critical for good performance in these manipulation domains. We also report results on training with less data. We subsample 50% and 10% of each dataset and train Iris on these smaller datasets. We don't see a substantial performance gap from training with half the lifting demonstrations. However, all demonstrations are needed to achieve good performance on the CANS task. This suggests that the data requirements for learning a good policy seem to scale with task complexity, as we expect. Next, we visualize some learned policies. BC tries to directly imitate actions in each state, so it's extremely sensitive to suboptimal data. The BCQ baseline learns a value function. However, it uses that value function to extrapolate to unseen states, resulting in a bad out-of-distribution path. Iris is able to recover a straight line path from the start to the goal. Here you see the demonstration data paths in blue. The red path is the BC baseline, which gets sidetracked by the demonstration data and is extremely slow, as you just saw. The green path is the extrapolated BCQ path, and our paths are in orange. They're focused around straight line paths, and they're fast because of the selective reproduction of optimal behaviors. On the lift task, BC is extremely sensitive to suboptimal data and unable to learn even reaching. BCQ uses the learn value function and it allows it to reach, but the policy diverges after a failed grasp due to unseen data. Iris is able to selectively imitate behaviors from the dataset, leading to success. Baselines are unable to learn from the diverse crowdsourced Robotorque demonstrations. We found our factorization and goal condition imitation to be crucial for successful learning in this setting. Here's a roulette where you can see the low-level controller on the left and the current goal on the right. The low level is good at reaching the intermediate goals set by the high level. Both imitation and goal selection are running in closed loop. Iris is able to recover from bad states, as you can see in this example here. And even when Iris fails, it exhibits stable closed-loop behavior. Thanks for listening. For more information, visit our website.